Welcome back to AI.Code.Cast. Sometimes the most elegant solutions in code come from tackling those problems that seem almost impossible at first. And today we're going to be diving into one of those classic challenges, how to implement a queue using only stacks.
Oh, that's a good one. Yeah, it's a great example of how understanding those fundamentals of data structures can lead to some really creative solutions.
Exactly. So for anyone tuning in for the first time, let's recap what queues and stacks even are. Why is this challenge so interesting?
Sure, so a queue is like a line at the grocery store, right? First person in line is the first one to be served. That's the whole FIFO principle, first in, first out. Stacks, on the other hand, are more like a stack of plates. You can only add or remove a plate from the top. So the last plate you put on is the first one you take off. That's IAFO, last in, first out.
So the challenge here is to simulate that first come, first served behavior of a queue, but using only the last in, first out behavior of stacks.
Yeah, almost like trying to make a pancake dispenser, but using only like a plate stacker.
That is a great analogy. And it highlights that core problem, right? With a stack, we can only access the most recently added element.
Right.
But with a queue, we need to access the oldest element first.
Exactly. So how do we even begin to solve this? Let's just start with the most straightforward approach. Let's just try to use one stack.
Okay, so if we only have one stack, we can easily add new elements, right?
Yeah.
It's just a simple push operation. But what happens when we need to remove an element from the front of the queue? That dequeue operation.
Yeah, that's when it gets kind of tricky. To get to that oldest element, which is all the way at the bottom of the stack, we would have to pop off all the other elements first. It's like unloading an entire truck just to get that one box you need at the very back.
Yeah, that doesn't sound very efficient at all,
Okay.
especially if our queue has a lot of elements.
Exactly. And in fact, that would give us a time complexity of O for Dequeue, where N is the number of elements in the queue. So that means the time it takes to dequeue grows linearly with the size of the queue, which is definitely not what we want.
Okay, so the single stack approach is a bust. So is there any way to get around this limitation, achieve a more efficient solution?
I mean, there has to be some kind of trick.
There is. And this is where it gets really fun. The key is using not one, but two stacks.
Two stacks. Okay, I'm intrigued.
So how does adding another stack solve our problem?
Well, think of it this way. One stack is going to act as our input stack. That's where we'll push all the new elements. We'll call this one S1.
Okay, S1. That's pretty straightforward. So what role does the second stack play? We'll call it S2.
Right, so S2 is going to be our output stack. And this is where it gets interesting. Whenever we need to dequeue an element, which means we're getting the oldest element, we're going to use S2 to actually help us reverse the order.
Reverse the order. Now I see why we need that second stack.
Uh-huh.
It's like we're using S2 to flip the pancake stack over
Yeah.
so we can access the bottom one.
Exactly. That's a perfect way to visualize it. So how do we actually use these two stacks to implement those queue operations?
Well, for onQueue, which is adding a new element to the back of the queue, we can just push it onto S1.
Right.
But for Dequeue, which is removing the oldest element from the front of the queue, it seems like we need to do a little bit more work.
Yeah. To dequeue, we'll first check if S2 is empty. And if it is, we'll transfer all of the elements from S1 to S2, and that effectively reverses their order.
So now the oldest element, which was at the bottom of S1, is now sitting at the top of S2, ready to be popped off.
Precisely.
Okay.
And once we've done that initial transfer, all the subsequent dequeues become really simple.
Okay.
We just pop from the top of S2 until it's empty again, and then we just repeat that transfer process.
This is starting to make sense. But I have a feeling we might be doing a lot of unnecessary work. Like, what happens if we push a bunch of new elements onto S1 after we dequeue? Do we have to transfer everything back to S2 again right away?
That's a great question, and it gets to the heart of why this approach is actually efficient. The key is to be a little lazy when it comes to transferring the elements. We only move elements from S1 to S2 when S2 is empty, and we actually need to dequeue or peek at the front element.
So it's like we're delaying that potentially expensive transfer operation until it's absolutely necessary. It's like we're only flipping the pancake stack when we're about to run out of pancakes on our plate.
Exactly. That's a great way to think about it. And this lazy approach is what makes the two-stack solution quite efficient. But to really understand why we need to look at the concept of amortized time complexity.
Okay, amortized time complexity. Now that sounds a bit intimidating, but I have a feeling this is the key to understanding why this two-stack approach is as clever as you say it is.
Yeah. Amortized analysis is all about looking at the average performance of an algorithm over a series of operations. rather than just focusing on the worst case scenario for a single operation.
So it's kind of like, sure, sometimes we have to transfer a whole bunch of elements between the stacks, but in the grand scheme of things, it doesn't happen that often, so the overall performance is still pretty good.
That's a great way to put it. Imagine like a toll booth on a highway, right? Sometimes you might hit a backup and you have to wait a while, but most of the time, you sail right through. The occasional delays don't change the fact that, on average, the toll booth keeps the traffic flowing pretty smoothly.
Okay, I like that. So how does this apply to our two-stack queue implementation?
Well, the potentially expensive operation is transferring all those elements from S1 to S2, but remember, we only do this when S2 is empty, and once we've transferred those elements, all the subsequent dequeues and peaks become super fast.
Because we're just popping elements off the top of S2, which is already in the correct order.
Exactly.
It's like having a plate of pancakes already arranged perfectly and ready to be eaten.
Exactly. So even though a single Dequeue operation might take ON time, in the worst case, over many operations, the average cost per operation is actually O1, which is what we want for a queue.
So we've achieved amortized constant time for both DQ and peak. Pretty impressive considering we're using stacks, which are inherently LIFO. This whole lazy transfer strategy really paid off.
Yeah, it did. It highlights a really key principle in algorithm design. Sometimes delaying an expensive operation until it's absolutely necessary can lead to some significant performance gains in the long run.
Yeah, it's all about picking your battles, right?
Yeah.
But before we get too carried away celebrating our amazing queue implementation, I have one more question. You mentioned the space complexity of this approach is ONN. Can you remind me what that means and why it's important to consider?
Sure. So space complexity basically refers to the amount of memory our algorithm uses. And in this case, ON means that the amount of memory we need grows linearly with the number of elements in the queue.
So if our queue doubles in size, we need roughly double the amount of memory. That makes sense. But why is it something we should care about?
Well, it's important to consider space complexity because memory is a finite resource, right? If our algorithm uses too much memory, it could slow down the entire program, or in some cases, even cause it to crash.
That's a good point. So in this case, our two-stack queue implementation uses ON space because, in the worst case, we might have all the elements stored in both stacks.
Precisely. And while linear space complexity is often acceptable, especially for smaller queues, it's definitely something to keep in mind if we're working with very large data sets. There might be alternative data structures or algorithms that could be more space efficient.
It's all about finding the right tool for the job, right? Now, I'm curious, are there any other approaches to solving this queue with stacks problem? Or is the two-stack method with that lazy transfer the gold standard?
The two-stack method is definitely the most common and efficient solution out there. It's elegant, relatively easy to understand, and, like we discussed, achieves that amortized constant time for those key queue operations.
But you know me, I always love to explore different perspectives. Are there any other approaches, even if they're not as efficient, that might offer interesting insights or trade-offs?
Well, if we're talking about alternative approaches, there's one that's worth mentioning, even though it's not really that practical. It involves using a single stack and recursion.
Recursion. Now that sounds intriguing, but potentially messy. How would that even work?
So the idea is to use recursive function calls to kind of simulate the behavior of transferring elements between two stacks.
Hmm.
We would push elements onto the stack for onqueue, and then for dequeue, we would use a recursive function to pop elements off the stack until we reach the oldest element.
So we're using the call stack as our second stack. Okay, that's a pretty clever hack.
It is clever, but it also comes with some downsides. Recursion can be very tricky to understand and debug, and it can lead to Stack Overflow errors if the queue gets too large.
Right, the call stack has its limits. So while the recursive approach might be interesting from like a theoretical perspective, it's probably not something we'd want to use in a real-world application.
Exactly. More of a thought experiment than a practical solution. But it does illustrate that there are often multiple ways to approach a problem, even if some are more efficient than others.
So it seems like the two-stack method, with its lazy transfer and amortized constant time complexity, is the clear winner for implementing a queue using stacks.
Yeah, I'd agree with that. It strikes a really nice balance between efficiency, simplicity, and practicality.
And it's a beautiful example of how understanding those fundamental properties of data structures and a bit of clever algorithm design can lead to some really elegant solutions.
Couldn't have said it better myself. And who knows, maybe our listeners will be inspired to come up with their own variations or improvements to this classic problem.
I wouldn't be surprised. There's always something to explore and discover in algorithms and data structures. There's always something new, right? But for now, let's wrap up this part of our deep dive. We've talked about the basics of queues and stacks, explored the challenges of implementing one using the other, and arrived at a pretty elegant and efficient solution using two stacks and a lazy transfer.
And we've learned about the importance of amortized analysis
Right.
and how considering the average performance over time can reveal the true efficiency of an algorithm.
It's all about that big picture sometimes. So in this deep dive, we really got to the core of how something like a queue can even be built with stacks.
You know what's really fascinating about this problem to me? It really highlights just how interconnected all these different data structures really are.
Yeah, it's not always about using just one data structure in isolation. Sometimes those really creative solutions come from combining them
Hmm.
and adapting them, and sometimes in unexpected ways.
Exactly. It really just underscores the importance of understanding the strength and weaknesses of each data structure, like we saw today. Stacks, while seemingly limited by that LIFO nature, can be manipulated to achieve the FIFO behavior of a queue.
It's a great reminder that limitations often breed innovation. If we had just assumed that stacks were completely incompatible with queues, we might have missed out on this whole elegant solution.
Absolutely. And this whole problem-solving approach, taking something that seems really restricted and finding ways to make it work for a totally different purpose, that's applicable way beyond queues and stacks. You see that all the time in software development, really, in any field, right?
It's like that saying, necessity is the mother of invention. Sometimes the constraints we have force us to think more creatively and come up with ingenious solutions.
Exactly. So to our listeners out there, embrace those constraints, those seemingly impossible problems, because that's where the magic happens.
Yeah. Now, before we wrap up this episode of AI.Code.Cast entirely, is there anything else that you think our listeners should take away from our deep dive into implementing a queue using stacks?
I think the biggest takeaway is the power of amortized analysis. It's such a crucial concept to understand when you're evaluating the efficiency of algorithms,
Yeah.
especially when you're dealing with operations that might have those occasional spikes in complexity.
Right. And it's so easy to get fixated on just the worst case scenario and dismiss an entire solution as inefficient. But amortized analysis lets us see the bigger picture. It helps us understand that those occasional expensive operations might be outweighed by all those fast and efficient ones.
Yeah, exactly. It's like judging a restaurant based on like the longest wait time you ever experienced. You might have had to wait an hour once, but if every other time you went, the service was really quick, it's probably still a pretty good restaurant overall.
That's a great way to put it. So to all of our listeners out there, remember that amortized analysis can be your secret weapon when evaluating algorithms. Don't just look at those worst case scenarios. You got to consider the average performance over time. And you might be surprised at how efficient some seemingly complex solutions really are.
And on that note, I think we've covered just about everything there is to cover on implementing a queue using stacks. It's been a really cool journey exploring the intricacies of those fundamental data structures and discovering all the clever ways they can be combined to achieve unexpected results.
It has been a lot of fun. So to our listeners, we really hope you've enjoyed this deep dive as much as we have. And we encourage you to keep experimenting, keep learning, and keep pushing the boundaries of what's possible with code.
And until next time, happy coding.
So in this deep dive, we really got to the core of how something like a queue can even be built with stacks.
You know, what's really fascinating to me about this whole problem is how interconnected all these different data structures really are.
It's not always about using just one data structure in isolation. Sometimes the most creative solutions come from, combining them and adapting them in sometimes unexpected ways.
Exactly. It really underscores the importance of understanding the strength and weaknesses of each data structure. Like we saw today, stacks, while seemingly limited by that LIFO nature, can be cleverly manipulated to actually achieve that FIFO behavior of a queue.
It's a good reminder that limitations can often breed innovation. If we had just assumed that stacks were completely incompatible with queues, we might have missed out on this whole elegant solution.
Absolutely. And this problem-solving approach of taking something that seems really restricted and finding ways to make it work for a completely different purpose, that's applicable way beyond just queues and stacks. You see it all the time in software development, really in any field.
Yeah, like that saying, necessity is the mother of invention. Sometimes the constraints that we have actually force us to think more creatively and come up with more ingenious solutions.
Exactly. So to our listeners out there, I encourage you to embrace those constraints, those seemingly impossible problems, because that's often where the real magic happens.
I love that. Now, before we wrap up this episode of AI.Code.Cast entirely, is there anything else that you think our listeners should take away from our deep dive into implementing a queue using stacks?
I think the biggest takeaway is the power of amortized analysis. It's such a crucial concept to understand when you're evaluating the efficiency of algorithms, especially when you're dealing with operations that might have those occasional spikes in complexity.
It's so easy to get fixated on the worst case scenario and dismiss an entire solution as being inefficient. But amortized analysis allows us to see that bigger picture,
Yeah.
to understand that those occasional expensive operations might actually be outweighed by a multitude of fast and efficient operations.
Exactly. It's like judging a restaurant based on the longest wait time you ever experienced. You might have had to wait an hour once, but if every other time you went, the service was super quick, it's probably still a pretty good restaurant overall.
That's a great way to put it. So, to our listeners, remember that amortized analysis can be your secret weapon when it comes to evaluating algorithms. Don't just look at those worst-case scenarios. You got to consider that average performance over time. And you might be surprised at how efficient some seemingly complex solutions can actually be.
And on that note, I think we've covered just about everything there is to cover on implementing a queue using stacks. It's been a really fascinating journey, exploring those intricacies of these fundamental data structures and discovering all the clever ways they can be combined to achieve unexpected results.
It has been a lot of fun. So to our listeners, we hope you've enjoyed this deep dive as much as we have. And we encourage you to keep experimenting, keep learning, and keep pushing those boundaries of what's possible with code.
And until next time, happy coding.